Let's see it in action. Let's do some linear regression on global average temperature data, according to NASA. These data are yearly averages, but I wanted to use the most up-to-date available data, so the years which are averaged go from May through the following April. This is May through April, annual average, global average temperature, according to NASA, from 1970 up through 2015. Well, we can follow the procedure using all the arithmetic and do all the computations by hand, but it's a lot easier if you use a computer program to compute it, which I did. I used R, which is excellent statistical software. When I do, it calculates what the best fit straight line is by calculating what the parameters are, and it gives me this. You can see quite plainly that the straight line it calculates fits the data pretty well. We would be interested in how different the data are from this straight line model. We can do that by calculating the residuals and making a graph of them over time. And here they are. These residuals look reasonably like random noise. There is the fact that the most recent value from May 2015 through April of 2016 is the highest, but it's not so high that there's strong, reliable evidence yet of any change or any departure from following a straight line. Now, our model wasn't just that it's a straight line. Our model is that it is following a straight line plus white noise. The residuals are an estimate of the noise. Are they white noise? Well, let's calculate the autocorrelation using the sample autocorrelation function, the Yule-Walker estimate. That gives us this for lags from 0 up to 16. The autocorrelation at lag 0 is equal to 1, as it always is. The autocorrelation for higher lags is mostly within the 2 standard deviation limits, which are displayed by these dashed blue lines. There is one here at lag 5. It stretches outside the 95% confidence limits a little bit, but that's not really such a surprise. Random variables are going to go outside the 95% range, well, about 5% of the time, just by random accident. Now, this is an eyeball test. It's not a strict statistical test. There are statistical tests to determine whether or not your autocorrelations are statistically significant. We'll get into that in future lessons. There's one called the Box-Young test. There's another called the Box-Pierce test. I applied them to these residuals, and they told me no, there's not sufficient evidence to say these are not white noise. So they could not reject the null hypothesis of white noise. Just for your own information, I can tell you from other knowledge I have that these residuals actually aren't pure white noise. There is some autocorrelation present, but it's weak. It's small enough that you can't really detect it and confirm it with this limited data sample. Here's another sample of data, same thing, May through April, annual average, global average temperature according to NASA. But instead of starting in 1970, I've included data all the way back to 1950. What would happen if we fit a straight line to this? Well, if you fit a straight line, you're going to get a straight line. And it looks pretty good, although it looks like maybe it deviates on the high end early, on the low end around 1970. Hard to be sure just by looking at a graph. We can look at the residuals, the difference between the data values and the straight line values, and they kind of reinforce this idea that the actual data were above the straight line early on and below the straight line after that, and then kind of came back to the straight line and then went up at the end. Once again, however, we'd want to have some kind of test for that. We could take these residuals as representing the noise and test for autocorrelation. Here is the sample autocorrelation function, the Yule-Walker estimate. This time, the very first lag 1 autocorrelation estimate is well above the 95% confidence limits, enough to make me think, this is probably not white noise. I can also apply the Box-Pierce test or the Box-Young test, and they both reject the null hypothesis of white noise. So there is strong evidence that these residuals are not just white noise. There are two ways that can happen. One is the residuals could be purely stochastic, but a kind of noise process that is not white noise. We'll have a lot to say about that kind of noise process in future lessons. The other way is that there's signal present that we have not removed by removing a straight line. Maybe the signal, the deterministic part, is deterministic, but it doesn't follow a straight line. If that's the case, then when we remove a straight line, we're not going to have removed all of the signal, so the residuals will not just be white noise because they won't be just noise. We could try other models. I haven't gotten into how to fit other models yet, and we will in future lessons. But for the moment, just take my word for it that it's not hard to do. Here is a quadratic model fit to the residuals. This quadratic model fits quite well, at least by eye. As a matter of fact, it also fits well when doing statistical testing. So this is some confirmation that maybe there is a trend which is not just a straight line in temperature data since 1950. I can look at the residuals from this quadratic fit, and they look very much like white noise. There's no more visual indication of departure from white noise. I can compute the autocorrelation function. There's a little bit of departure, but it's not a lot. It's at higher lags, and the Box-Pierce test says cannot reject the idea of white noise. It's plausible from these data that the residuals of that fit are just white noise. So that means we have another model for the data from 1950. It is a model which is quadratic function of time, where it is increasing over time, but the rate of increase has been going up. Now I can tell you that this is a good model, and with just this limited data set, it's hard to say that it's not the best model, although there is other data available which indicates that it is not the best model available. Nonetheless, we have been able to show that global temperature is rising. If you look at just the temperature since 1970, there's no way to tell that it's departed from a straight line. But if you look at the data since 1950, we can be quite confident that it is not just a straight line plus white noise.